Welcome back, everybody. So we're going to finish up section 4 for today, indeterminate forms and Lafital's rule. Now, remember what we were talking about yesterday. We had these limits that we couldn't really compute. And again, just as a reminder, this is kind of like an oddly placed lesson in that, we could have learned this lesson at the beginning of. It's not dependent on the first 3 sections of this chapter. We could have learned this right at the beginning of chapter 4. We could have learned this at the end of chapter 4. This is kind of like a weird, kind of like a sidestep. Okay. Basically, what we're saying here is that if you have an indeterminate form of the form 0 over 0 or infinity over infinity, and looking at this limit here, that's like, okay, if I plug in 1 here, that would be a 0. If I plug in 1, 0. Okay, we have an indeterminate form of the 0 over 0. Now, remember that this is not saying, like, if you get a number over 0, that is not an indeterminate form. Okay? So if you have something like, I'll put it on the board here. If you have something like x, like 2x plus 1 over x, and I want to find the limit as x goes to 0, right? That is not an indeterminate form. And the reason it's not, even though the limit does not exist, it's not an indeterminate form because if I plug it into the numerator, I get 1, not 0. You cannot use Lafital's rule if it does not have an indeterminate form. 0 over 0, infinity over infinity. Like this one, if I plug in ln of 0, I get 0. If I plug in x minus 1, 0 minus 1 is 0. That's why it's an indeterminate form. So be careful of that. And we said, Lafital's rule says that if you have an indeterminate form of 0 over 0 or infinity over infinity, that means that you can take the derivative of the numerator and the derivative of the denominator. Remember, it's not using quotient rule. That's not what we have here. It's not quotient rule. You're taking them separately. It's a common mistake that I always see. People trying to use quotient rule with this. You have to take the derivative of the top divided by the derivative of the bottom, and then you can plug it in. And remember that we had examples where we had kind of like a Lafital's rule inside another Lafital's rule, right? We said, I think it was, I can't remember which one. I think it was this one. Maybe the one, no, it was the one before. It was this one, the one with the e to the x. There were actually 2 Lafital's rule in there, right? Because we ended up with e to the x over 2x, and if we plug in infinity, it was still another indeterminate form. So we could use it again, and then we would know that it would be infinity. Okay, and then we just had some examples, and let's do. I want to do this trig one. Let's do. There was one with tangent or something in it.
I'm gonna say this.
Where did it go?
I hate trig.
Oh, that's no, that's
it's the trig.
Oh, this one. Okay, there we go. Let's do this one. Find the limit as x approaches 0 of tangent of x minus x over x to the third. Tangent of x minus x over x to the third. This is kind of a tricky one. I will say that. I'm gonna start off by saying that this is a little bit of an odd one. Okay, I guess the first thing that we should check is it an indeterminate form? The limit as x goes to 0 of tangent of x minus x. Let's evaluate that. Okay, so what is tangent of 0 minus 0? Okay, tangent of 0 is 0, right? Which makes sense. Think about the coordinate at 0 degrees. It's 1 comma 0. Y over x would be, it would be 0. Just trust me here. It would be 0 minus 0 or 0, right? And then we would have the limit as x goes to 0 of x to the third, which again is 0. So we have an indeterminate form, 0 over 0. Indeterminate 0 over 0. And again, I'm going to abbreviate like that. So if I call it an indeterminate form, you can just do like IND. Just make sure you tell me which one, whether it's 0, 0 or infinity over infinity. It doesn't matter which one, because in the end, I'm going to use the derivative here, this Lafital's rule. Okay, so tangent x minus x. The derivative of tangent, I'm just going to cheat here and use my formula sheet again. The derivative of tangent is secant squared. Okay, so we're going to find the limit as x goes to 0. Remember, that does not change. The limit as x goes to that number, that stays the same each time for Lafital's rule. So we've got secant squared minus the derivative of x is just 1 over 3x squared. Questions there? All right, so let's see what we get here. I'm going to say, let's see if the Lafital's rule happens again. Secant squared x minus 1. Let's plug in 0. Because why am I checking that? Because I'm looking at the denominator thinking, uh-oh. Okay, look at that. That's not good. If I plug in 0, I'm going to get a 0 on the bottom. So either this does not exist or whatever. Maybe it's another indeterminate form. So secant, now remember, what is secant? 1 over cosine, right? So this is 1 over cosine squared, cosine of 0 squared minus 1. Okay. So that's another 0. The limit as x goes to 0 of 3x squared is 0, obviously. So this is another indeterminate form. I did that in there.
Oh,
yeah.
Got it. Okay.
Indeterminate form of 0 over 0. Okay, so now we say, the secant squared, that must have just been 1 to get a 1 minus 1. The limit as x goes to 0. So this is Lapital's rule inside a Lapital's rule inside a Lapital's rule, right? That's what we got here. All right, now in the denominator, this is really easy. That's just going to be a 6x, right? Okay. The derivative of the numerator. What's going to happen when I take the derivative of minus 1? That's going to go away. So let's remind ourselves what d over dx of, let's move that down a little bit. D over dx of secant squared x is. Remember, that's like saying d over dx of secant of x squared, right? What do I have to use when I find the derivative there? Chain rule. So this is 2 times secant x times, right? That's just taking the derivative of the squared, right? The derivative of the squared pulls the 2 out in front. I'm not changing the base. Pulls the 2 out front, kicks the power down. We've peeled away the layer of the squared, and now we take the derivative of the inside. Well, the derivative of secant is secant x tangent x. Okay, the derivative of secant is secant x tangent x. Okay. Let me grab my notes real quick. I just want to make sure that I'm on the same track. Please. Yeah. So I'm at here. Okay. So now I can combine. Yeah, that's what I just wanted to make sure that I can do this. So on the top, this is going to be 2 secant squared x tangent x. Okay? I just multiplied these together. Now, I guess we should see if this is going to be another indeterminate form. Okay? Because I'm looking at the bottom thinking, uh-oh, again. Right? Let's see what that's going to be. Well, if I have secant, the bottom's going to go to 0. If I say secant squared, that is going to be 1 over cosine of 0 squared, and then times tangent of 0. Okay, I could get another indeterminate form here, right? I could get another indeterminate form, but I'm actually going to break this apart a little bit. Okay, watch here. I'm going to do some simplification because honestly, there's a lot of parts going on right here, right? I see secant squared. I see tangent x. So maybe there's things that are indeterminate, and maybe there's things that are actually computable. Here's what I mean by that. Now, what do I have here? I have a 2 over 6, right? Remember that I can remove a constant out front. So I'm going to say that, I've got 1/3 times the limit as x goes to 0 of secant squared x tangent x over x. Now, watch what I'm going to do here. I'm going to remove the secant squared, okay? And I'm going to treat it as a product of two pieces here. So I'm going to say 1/3 times the limit as x goes to 0 of secant squared x times the limit as x goes to 0 of tangent x over x. Because we can do that. We can break apart the limit like that if we would like to. And all I did was just remove the secant squared x out front. Now, what is the limit as x goes to 0 of secant squared x? We've been running this a couple of times here. So 1 over cosine squared, cosine 0 squared. That's 1, isn't it? So this reduces to 1. So this is 1/3 times 1 times the limit as x goes to 0 of tangent x over x. See, what I'm doing there is I'm simplifying it down a little bit. But now look at my last piece here. What was tangent 0? Tangent 0 was 0. See, look what I'm doing here. The limit as x goes to 0 of tangent x is 0. The limit as x goes to 0 of x is 0. So I just showed that this is the piece that was giving us the indeterminate form. Okay, so this is indeterminate of the form 0 over 0. So what I can do is say 1/3 times the derivative of the numerator divided by the derivative of the denominator. The derivative of the numerator, the derivative of tangent x. Did I leave it over? Where is my cheat sheet? Can we just do this as a secant squared? Oh, sorry. Yeah, secant squared x. So this is the limit as x goes to 0 of secant squared x over, what's the derivative of x? 1. And we've done this like a million times. What do I get when I plug in 0 into secant squared? I get 1. So this is actually just 1/3 times 1, or 1/3. Ooh, that was a fun one. That was a good one. The weird part about that one was pulling this secant squared off the numerator and pulling the 1/3 out, right? I get that. I'm just doing this problem to remind you that there are different things that you can do with limits. You can break them apart if they're products. You can pull out constants if you need to. There's a lot more things you can do with a limit that you couldn't do with other things. Yes?
Would it still have worked if you had without secant squared?
Yes, but then the derivative would have been really weird, right? Think about taking the derivative of secant squared x tangent x. You have a product rule with a chain rule in it.
Mm-hmm.
You know what I mean?
Yeah.
So it was better to reduce it because we know what the limit of x goes to 0 of secant squared x is. It was just 1 because we've done it so many times. So then we could remove it and then reduce down the piece that was giving us the fit, you know? Just the weird part was the tangent x over x.
Yeah.
That was the weird part so that we could remove it and work with it differently.
So why didn't you pull out secant squared of x over x?
Because that would still have gotten me a weird thing, having it over x. The limit as x goes to 0 of secant squared over x would have been a 1 over 0.
So you can
And then it would have been almost like the limit did not exist, which is...
So you can just pull whatever you want out of it.
Right, you can break pieces apart in different ways.
Okay.
The reason why we broke it apart in this way is because this we knew.
Mm-hmm.
And then this piece in here was giving us the indeterminate form.
Okay.
That makes sense?
Yeah.
Yeah. Okay, let's do this one. Do another trig one. The limit as x goes to pi from the left of sine x over 1 minus cosine x. Now, just as a reminder, Lafital's rule works with one-sided limits. Okay, Lafital's rule works with one-sided limits. Now, I'm going to show you something here. Go with me here. What's the derivative of, thinking about it this way? This is what I want to show you here. I'm almost tempted to, hold on a second. Oh yeah, I don't want to do that. That's right. If I were to think that, like, oh, this is an indeterminate limit, and I go straight to using Lafital's rule because I see something that looks like it might be using Lafital's rule. If I took the derivative on the top, what's the derivative of sine? Cosine. And then what's the derivative of the bottom? Well, derivative of 1 goes away. What's the derivative of negative cosine? Positive sine, right? And we said, okay, let's try to calculate the limit of pi from the left of this. Well, what is cosine over sine? Cotangent. Cotangent, right? So this is essentially like saying the limit as x goes to pi from the left of cotangent of x. Okay? And then we would say, okay, well, maybe 1 over tangent of pi gives it to us. And then we might be, not inverse tangent, 1 over tangent of pi. There we go. I was going to say this should not work. It's going to divide by 0. So I might be tempted to say, oh, that this is maybe an indeterminate form, and we might have to work with it a little differently. Now think about this. If I go into my y equals and I graph 1 over tangent of x, zoom 6, that's just the graph of cotangent, right? And we would say, okay, what's happening at pi from the left? We would say, okay, 3.14, right around there. Where does it go from the left side of that boundary line? Negative infinity, right? We might be tempted to say, oh, then that should be negative infinity. Tempted. Why do I say this? Because you must always check the premise of, now what is that? If I plug in 0 into sine, sine of x, sine of pi. Oh, no, I'm sorry, not 0. Pi. If I take sine pi, I get 0. And I take the limit as x goes to pi, forgive me for not writing on the left, 1 minus cosine x. You might be thinking, oh, that's going to be 1 minus 1 is 0, right? 1 minus, come on now, 1 minus cosine pi. That's not an indeterminate form. I actually get 2, right? So what is this full limit? That's just 0. 0 divided by 2 is just 0. We could have just done direct substitution from the very beginning. I went way off in the distance using Lafital's rule when I should not have even gone there from the beginning. Okay? The reason I say this to you is because there might be some problems like that hidden in the homework where you might jump to Lafital's rule when you should never even gone there because it did not meet the premise of Lafital's rule. It has to be of that indeterminate form, 0 over 0 or infinity over infinity. This was extra work that we never even needed to do because we didn't think through the hypotheses. Make sense? I have. Hold on a second, let me get Hunter's. When I go in the hallway?
Yep.
All right. The last couple things I wanted to talk about are other ways you could get an indeterminate limit or a indeterminate form. Okay, because what you can do is actually manipulate the function at the very beginning to make it an indeterminate form. Okay, like what you can do is if you've got f times g or g times f, what you could do is put it into the denominator and then write the reciprocal of it. Like, what do I mean by this? Think about reducing this down. If f divided by 1 over g was what I was using here, well, isn't that like saying f times the reciprocal of 1 over g. Well, what's the reciprocal of 1 over g? G, right? So, and I could do that with either function. So what we can do is actually write it out in a different way so that we get a different indeterminate form so that you can use Lafital's rule, okay? So you can rewrite certain functions to make them fit Lafital's rule. When they normally might not have, you could kind of work with it a little bit to see if you can. Other indeterminate forms, there are indeterminate powers as well, okay? These are all in the notes for you guys if you need them. The last part of the homework is saying, okay, is this an indeterminate form? So you might want to reference this back again. There are several other types of indeterminate forms. Like these are indeterminate powers. Like if you get a f of x to the g of x, this is a 0 to the 0 type, right? If somehow you plug in a, you get 0. You plug in a to g, you get 0. That's the form 0 to the 0. This is a form infinity to 0. That's another indeterminate form. And then also 1 to infinity. That's another indeterminate form. Okay, so these are just other indeterminate forms that you may use or they may be asked about. And then there's also indeterminate differences as well. Okay, if you've got two functions where you're subtracting from one another, and you plug in x goes to a of f of x and you get infinity, you plug in x goes to a of g of x, you get infinity, you end up getting infinity minus infinity. That is an indeterminate form. Infinity minus infinity. Now be careful, 0 minus 0 is not an indeterminate form because what is 0 minus 0? 0. Okay, it's definite. Okay, so if you get two functions where they're subtracted from one another, and they both end up going to infinity, that is another type of indeterminate form. Let me show you an example of one taking the reciprocal problem. We'll do this one, and then that'll be it for today. The limit as x goes to 0 from the right of x ln of x. Okay, now do you notice how this is a product of two pieces, two functions, x and ln of x. See, what I can do here is manipulate one of the two so that you can get it into an indeterminate form. Like what I mean here, I could take this as the limit as x goes to 0 from the right of ln of x over 1 over x. You follow me there? All I did was take the reciprocal of x, which would be 1 over x, and I put it into the denominator. Because if you put it into the denominator and take the reciprocal, those are kind of like things that undo each other. It would get us back to just x. Could I have done this with ln? Of course. That would be fine. But the problem is, when I go to take the derivative later on, I don't want to try to take the derivative of 1 over the ln of x. That might get a little confusing. Okay. All right, so let's take the premise of Lapital's rule. Okay? The limit as x goes to 0 of ln of x. Well, and we're saying on the right. Ln of x. Well, if I plug in 0 again, I get 0. Okay. Now, take a look here. This is x, the limit as x going to 0 of 1 over x. Okay. This looks like it's not going to exist, right? So it's kind of, it's not infinity over infinity. I'm going to say it's still of that form, indeterminate form 0 over 0. Okay. Because we had to manipulate it like that, it's still going to be of that indeterminate form 0 over 0. Because it's still of that over 0. See what I mean there? If I plug in 0, it's still going to be like 0 in the denominator. Now, so what we can do is apply Lapital's rule. The limit as x goes to 0 from the right of 1 over x, the derivative of ln of x is 1 over x. And this piece in here is like x to the negative 1, right? All right, so this is negative 1 x to the negative 2. Negative 1 x to the negative 2. Which is essentially like saying 1 over x divided by negative 1 over x squared, right? That's x to the negative second power. So let's try to manipulate it down and see what we can do with it. 1 over x, and let's change it into multiplying by the reciprocal, times the negative x squared over 1. Okay, so this is x squared, negative x squared over x, which is just negative x. So we can say that the limit as x goes to 0 from the right of negative x is 0. And there's my answer. Okay. So you can manipulate one of the two functions. Could I have done this entire process by flipping ln of x? Yeah, that would be completely fine. Just go with the simpler one to find the reciprocal of. It'll really help you out in the long run. Okay. Questions on any of that? A majority of the homework, I know I talked a lot about these indeterminate forms at the end and all the different types. I would say 80% of the homework is just using Lafital's rule, making sure you can use it and then using it. Okay? Because that's the important piece of this section anyway. All right. Let's be done for the day.